Hello mathematicians, thank you for joining me today. We're going to go through now and find all asymptotes, that is vertical and horizontal asymptotes of the function x squared plus 3x minus 4 over 2x squared plus x minus 3. Before I actually find the asymptotes of our function, what we'd like to do is recall what the asymptotes are. So what we have is we have a vertical asymptote if our function looks like a vertical line. So I've drawn in the vertical line x equals c and dotted white here. And this function looks like that as x gets close to c because the line here is going to get closer and closer to this. It's going to approach this value. And as we get closer to this, this will look like a vertical line. Same thing on this end is that will look like a vertical line. So it'll look like the equation x equals c close to c. And so that's how we know that there's a vertical asymptote. And so what we're really trying to say here is that notice that as we get close to c, the y values are getting arbitrarily large, or the y values are getting arbitrarily large in a negative direction. And so either way, what we have is that there is a vertical asymptote if the limit as x goes to c, either from the right or the left, is equal to either positive or negative infinity. So if we want to find vertical asymptotes, what we have to find are all the places where the limit is equal to either plus or minus infinity. But recall that means that the limit does not exist in such a way that it gets arbitrarily large in either a positive or negative direction. So what we need to do is we need to find those points. On the other hand, if we want to find horizontal asymptotes, we're going to say that our function is going to look like the horizontal line here, y equals k. And so now if we're going to approach that line, what's happening is that eventually our function is going to become horizontal. And so what we're noticing is as we're looking at this, because we have this horizontal asymptote, as my x values get arbitrarily large, my y values are going to get close to this k value. Same thing over here is as my x values get arbitrarily large in a negative direction, despite the bouncing up and down, I'm going to get closer and closer to y equals k. So I'm going to say here that I have a horizontal asymptote at y equals k because my function approaches the value y equals k as x either goes off towards infinity or x goes off towards negative infinity. So using my limits, I'm going to say that I have a horizontal asymptote if the limit as x goes towards either infinity of f of x is equal to some y value, let's say k, or the limit as x goes towards negative infinity of f of x is equal to k. So that is, if I want to find asymptotes, I'm really looking at limits. Either where is my limit equal to positive or negative infinity, or what is the limit as x goes off towards positive or negative infinity. All right, so now if we go back to our problem, we had f of x was this. If we want to find vertical asymptotes, remember that that's where the limit as x goes to c is equal to positive or negative infinity. As we discussed when we were looking at the picture, that means that the limit does not exist in such a way that it gets arbitrarily large in either a positive or negative direction. So now if we want to find vertical asymptotes, the idea is that the limit does not exist, therefore the function is not continuous at that point. Therefore, the only places I can have vertical asymptotes are places where I have discontinuities for this function. Now, since this is a rational function, we know the top's a polynomial, the bottom's a polynomial, so it's going to be continuous everywhere unless the bottom is 0. Therefore, if we're looking for vertical asymptotes, what we want to find is where is the bottom 0? These are going to be our potential asymptotes, and so then we'll have to determine from there whether or not they actually give us asymptotes. Alright, what we've seen is that we can have vertical asymptotes if the limit as x goes to some point is either plus or minus infinity. And so, because the limit is plus or minus infinity, we would say that the limit does not exist in such a way that we get arbitrarily large in the positive or negative direction. That means that our function would have to be discontinuous if it was going to have a vertical asymptote. So if we want to find potential vertical asymptotes, what we have to find are points of discontinuity of our original function. Now, because we have a rational function here, this is only going to be discontinuous if the bottom is equal to 0, because the top's a polynomial, the bottom's polynomial, so the only thing that would mess this up is if the bottom was 0. Therefore, in order to find potential vertical asymptotes, we find where the bottom is 0. Now, in order to do that, we would set 2x squared plus x minus 3 equal to 0. And now we have to solve a quadratic equation. We can do that either by factoring or by using the quadratic equation. Here this factors fairly nicely, so we're going to go ahead and do that. And so what we're going to get here is the product of the two monomials, where the coefficients in front of x have to multiply by 2, and the constant coefficients have to multiply to -3. So the reason why this is relatively nice is that the only factors of 2 are 1 and 2, so I know one of these is 2 and one of these is 1. And the only factors of -3 are -1 and +3, or +1 and -3. And so somehow one of these is going to be -1 and +3, or +1 and -3, and I might have to switch the order, but we know that the factors are going to end up looking something like that. So now to determine which one it is, we're just going to multiply and add together. So I know 2x times 1x is 2x squared, which works out. And I get 2x times 3 is 6x, minus 1 times 1x is 5x. We wanted positive 1x here, not positive 5x, so that didn't quite work out. So what we want to do is try another combination of these. So I'm going to switch these up, and I'm going to put a -1 here and a +3 here. And then what we'll notice is that, again, 2x times x is 2x squared. 2x times -1 is -2x. 3 times x is 3x. 3 minus 2x is 1x, so that works out. And 3 times -1 is -3. So we do get the factorization that we were looking for. Now that we've factored it and we've checked to make sure it's correct, we're going to say, okay, well, a product is equal to 0 if one of the terms is 0. So that means either 2x plus 3 is 0, or x minus 1 is 0. And so if I solve these, I get 2x is equal to -3, or x is -3 halves. And then solving this one, I get x is 1. So what we notice is that this function is discontinuous if x is -3 halves or x is 1. Therefore, these are the only points where I could have vertical asymptotes, so I've limited the places I have to check, but I still do have to check these to see if these are asymptotes or if something else is going on. Now, in order to determine if these are vertical asymptotes or not, what we have to find is the limit as x goes to those points. If that limit exists, then we know it's not an asymptote, but if that limit's either plus, minus infinity, or if we get 1 going each way, then we get that this limit does not exist, so we have a vertical asymptote. So now, in order to do that, we find these limits. So to start off with the limit, the first thing I'm going to do is I'm going to plug -3 halves in. So if I plug -3 halves in, I get -3 halves squared plus 3 times -3 halves minus 4 all over. And now the reason why I picked -3 halves is because the bottom is going to be 0. So instead of having to plug that all in over again, I'm going to just set the bottom equal to 0. So now I just need to calculate this. -3 halves squared is 9/4 minus 9 halves minus 4. And so then 9/4 minus 9 halves is -9/4 minus 4, which is 16/4, is going to be -25/4 divided by 0. And so when I plug this in, I get -25/4, all divided by 0. And so if I'm checking that, what's going to happen here is, notice this is not 0/0. If it was 0/0, we'd have to do more work because it's an indeterminate form. Because I get a number over 0, what this means is that as I get close to x equals -3 halves, the top is getting close to -25/4, whereas the bottom is getting arbitrarily small. It's getting closer and closer to 0. So what I'm doing is I'm taking that function value close to -25/4 divided by a extremely small number. What that means is that because this is getting arbitrarily small, and this is some number close to 4.25, if I divide by that, I get, well, this -4.25 divided by a very small number is a very large number. Whether it's positive or negative depends on which direction we're coming from. And so what's going to end up happening here is that one direction is going to be positive infinity, one's going to be negative infinity. So if I get a number over 0, I know one of the directions positive infinity or negative infinity. And so I know that I do have a vertical asymptote at x equals negative 3/2. So I do have a vertical asymptote, which I'm going to denote VA, at x equals negative 3/2. Now, on the other hand, if I do this at x equals 1, what I get is, well, if I plug in 1, I get 1 plus 3 is 4, minus 4 is 0. And then again, we know the bottom is 0. So when I plug in 1, f of 1 is going to look like 0 over 0, which means that my function is undefined, but my limit is indeterminate because I do have a 0 over 0. So I have to do more work. And what I'm going to do here is, well, this is a rational function. So if we go back to limits of rational functions, we know that we factor the top, we factor the bottom, and we've already actually factored the bottom. So I'm going to use that and say this was 2x plus 3 times x minus 1. Now, we know that if we plug 1 into here, we're going to get out a 0. So we actually know that an x minus 1 will factor out of the top. And so what we're left with checking is just what would the other one be. And so negative 1 times 4 would be negative 4. And then positive 4 minus 1 is positive 3. So that's going to work out. So I'm going to get x plus 4 as the other term in the factorization here. Now recall, because we're taking a limit, we want x close to but not equal to 1. So the x minus 1 over x minus 1 is just going to be 1 for all of those points. And what we get is the limit as x goes to 1 of x plus 4 over 2x plus 3. And so now what we've done is we've factored out the x minus 1 so that we have a new limit. If we calculate this new limit now, we would plug in 1 and I would get 5 over 5. 1 plus 4 is 5 over 5, which is precisely 1. Because that's a number, that means my limit is defined as 1. Therefore, the limit as x goes to 1 of f of x is equal to 1. So what does that mean? Well, that means that the limit exists. So therefore, we will not have a vertical asymptote. Indeed, what we will have here is a whole discontinuity. Now that I've found my vertical asymptotes, I want to find my horizontal asymptotes. And remember, the horizontal asymptotes are found by taking the limit as x goes towards positive infinity or negative infinity. So I'm going to take the limit as x goes towards infinity of f of x. And so what I'm going to do is I'm going to look at this function again, and I'm going to say, well, what happens as x goes towards infinity? So if we look at that as if we treated it like a number, we would say, okay, x is getting large, and then a large number squared is a large number, plus 3 times a large number minus 4 is still going to be a large number on top. And then we get 2 times a large number plus a large number minus 3 is still a very large number. So here what we end up with is, if I'm thinking about what happens as x goes towards infinity, I'm going to end up with an infinity over infinity. Now, infinity over infinity is one of those other indeterminate forms, so that means that we have to do more work here. In order to do more work, we have to find some way to simplify this so that we can actually take the limit. And so what I'm going to do is I'm actually going to take my function x squared plus 3x minus 4 over 2x squared plus x minus 3. And now I'm going to look for the highest power of x on top or bottom. So I want the highest power between both of them. And we notice is we have an x squared up top, we have an x squared on bottom. Because x squared is the highest power of x, what I'm going to do is I'm going to multiply by 1 over x squared on top and bottom. And notice now that 1 over x squared over 1 over x squared, these are the same thing. So as long as x is not 0, then this is still 1. So we don't have to worry about x being 0 because we're worried about large x's. So we can just assume x is larger than 0. And then what we end up with is, well, I'm really just multiplying by 1 here for the values I'm interested in, so I'm not changing the problem. Now the reason why this is going to be helpful is if I distribute that out, what I get is x squared over x squared plus 3x over x squared minus 4 over x squared, all divided by 2x squared over x squared plus x over x squared minus 3 over x squared. And now what I can do is I can do a little bit of simplification and notice that x squared over x squared is just 1. Again, as long as x is not 0, but we don't have to worry about that because it's large x's. 3x over x squared is just 3 over x. And I'm going to leave this as negative 4 over x squared. Same thing here, the x squareds will cancel, and I'm left with 2. And then I have x over x squared will simplify to 1 over x. And then I'm left with minus 3 over x squared. Now the reason why this is helpful is now I can think about, well, I have a new limit. What's going to happen as x gets large? And so I'm going to say, okay, well, as x gets large, 1 is going to stay 1. So this is going to look like 1 plus. And then I'm going to get 3 over a huge number. Now when we were talking about vertical asymptotes, we had 3 over an extremely small number was infinity. Well, now we're going to get 3 over a huge number is going to get arbitrarily small. So as a limit, this is going to be 0. And the same thing here, we're going to have 4 over a large number is just going to be 0. And then on bottom, the 2 just goes to 2, plus 1 over infinity is an extremely small number, so 0. Minus 3 over infinity is going to be an extremely small number, so that's just going to be 0. So what I end up with is 1 plus 0 over 2 plus 0. And so I get that this limit is indeed going to be 1/2. So I can say by multiplying by 1 over x squared, I was able to simplify this so that I get out that my limit is exactly 1/2. Notice that 1/2 is a number, and because I get a number out, that means that I will have a horizontal asymptote here. So what I'm going to say is that there's going to be a horizontal asymptote, or HA, at y equals 1/2. So before I had vertical asymptotes at x equals negative 3/2. Now I'm going to have a horizontal asymptote at y equals 1/2. That is, the y value is approaching 1/2 as x gets large. Now I should point out that you should also check the limit as x goes towards negative infinity. But if we do that here, we're just using negative infinity instead of positive infinity. This work's still valid, this work's still valid, and then if I plug in negative infinity, well, 3 over a very large negative number is just a very small negative number. So again, it's just going to be 0. And so what we're going to end up with is, again, 1/2. So in both directions, we'll actually have a horizontal asymptote at y equals 1/2. Thank you for joining me today. I hope you learned something and enjoyed the process. If you did, make sure to like the video and subscribe to the channel. It all helps to make sure that we can get this out to anyone else who needs calculus help.